for organizing this session in the Indian Science Congress. This is the first Indian Science Congress that I have come to, and it's a very different experience from the normal conferences that I go to, and it's enjoyable. And I thank the organizers for inviting me here and giving me this opportunity to talk about our work. So we have been working on these ideas of nonlinear, of metamaterial absorbers, resonant absorbers for the last 5-6 years, where we have realized absorbers with defined absorption band characteristics like heat absorption, bandwidth, what's the frequency at which the structure, metamaterial structure absorbs, and so on, in a very flexible manner right over the RF to optical frequencies. Today, we are now talking about such fine things that we are talking about nonlinear and switchable metamaterials. I will be presenting to you some very recent work we did on the nonlinear metamaterials, which have been published in the last 2 years. So, as I start, first of all, to many of you, you might be wondering what a metamaterial is. Let me give a definition of a metamaterial. Just like in metaphysics, meta means beyond here. So, metamaterials are materials that give you properties that are beyond normal materials. That is, they should have properties that are not usually found in natural materials. And you can induce these properties at will by design of the metamaterial. So, you have composite materials with structural unit cells which are much smaller than the wavelength of the light at which they interact. And these structural units combine to make a block of a material. Now, you think about that block of the composite. It's a composite material. There's a lot of structures inside, but you think of the whole block as a single homogeneous block. And you give it properties, and these properties, with how it will affect light, which actually goes through it, or microwaves, which actually are incident on it, you encapsulate all those effects in terms of the properties of that block. And these are what we call metamaterial properties. And these properties, it turns out, may have very little to do with what are the materials with which you make the material. Here, it is a structure that gives rise to most of these properties. And hence, when we make these structured composites, take a lot of trouble to make these structured composites, we expect that we will end up getting extraordinary properties out of this. And right from the beginning, we have always reasonably demanded that not only should the properties be very nice, they should be multifunctional as well, with different aspects of the structure carrying out different tasks. And so these were the ideas which actually changed the world. We look at optical and electromagnetic materials, and these ideas started at around 2000 at the turn of the last century. So as I said, the metamaterial structure is small compared to the wavelength. And then all of optics, electromagnetics, that there is something called a diffraction limit. The wavelength of light is, because it is a finite object, a finite number, it doesn't allow the light to see objects very closely. There are some features on an object which is much smaller than the wavelength itself. Alright? This is what is called the diffraction limit. So, in these metamaterials, where we have periodic structures, we would have Bragg scattering, but the Bragg scattered waves would all be evanescent. Evanescent waves are waves that don't propagate in space. They are stuck around the scattering object. They are just localized. So, if you put in a beam of light, you will get one beam of light which transmits, one beam of light which reflects on the composite. Suppose you make a slab out of this composite, you will get one beam which transmits, one beam which reflects. Even though there is a structure, because any of the scattered waves don't propagate. But these scattered waves, they change the way light interacts with these objects inside. So if there is a resonant response among these structural units, then that resonant response will be felt by the light, it knows that there is a huge amount of polarizable or magnetizable material inside this block. So those responses, the polarizability and magnetizability, you will encapsulate in the what are we call the effective material parameters. You think of this block of composite as an equivalent block of a homogeneous material. This we do all the time. If you think about it, you take a piece of glass. The glass has atoms and molecules, but for visible light, it is just transparent. We say that we never think of the atoms and molecules which make up the glass. But then it is the properties of the atoms and molecules which give rise to the refractive index, dielectric constant. That is because the wavelength of this visible light is very large compared to the atoms and molecules. On the other hand, if you make the wavelength small enough, like with X-rays, then it will see the structure inside. It will start scattering, and it will see a beautiful X-ray diffraction and so on from crystals. So here it is possible to think of it as a homogeneous medium because the structural sizes are small. And this gives rise to an exceptional simplicity. You see, very few effective medium parameters are all that are now necessary to describe a very complicated object. There are many complex shaped structures there could be, and you still don't need to understand how are the detailed manner of interaction of the electromagnetic fields with these objects. You only put all of them as a parameter. You parameterize all of those interactions in terms of these effective medium parameters. Now a design engineer can do wonders. With these parameters, you can design a lens, a waveguide, you can design practically any optical or electromagnetic device that you want to make. So what are those so-called unusual properties that we may talk about? Very large permittivity, permeability. These are important for microwave engineers. You can have zero permittivity, permeability. You can have extreme anisotropy. You can have anisotropy in crystals is typically very small. The refractive index contrast in two directions might be as small as 0.0 to 0.1. That's probably the largest you can get. But in metamaterials which are anisotropic, you can see very large difference. Along one direction, the polarizability can go to infinity, and on the other direction, it can go close to minus infinity. It can be that large. Now, you can also generate, because you will find, as I will show, we can control the electrical and magnetic responses simultaneously. You can do what electrical engineers call as perfect impedance matching. This will be one of the main things of today's talk. And the other thing that happens is, because you have microscopic structures, there are very large local field enhancements inside these. Now these are the two effects that I will be using for today's talk. One which is to independently control the electric and magnetic response to generate some impedance matching, various levels of impedance matching, and localized field enhancements, which means in those regions, if you put nonlinear materials, the nonlinear responses can be very large. This is something that we will do today, and the point is, metamaterials usually are limited in their applications because of dissipation, large levels of dissipation, particularly at optical. But if you desire that absorption is the end result that you want, then it becomes very nicely usable. You get lovely resonant bands which are very. So this is something that you would all have seen in a BSc textbook. How do you characterize the dielectric response of a medium? So you see, you would typically end up writing a four-stamped oscillator equation for the motion of an electron, which is bound to a center, atomic or molecular center, and which is forced by the electromagnetic field. So if you calculate its response, you will be able to write the polarizability in terms of the incident field, and then the polarization in terms of the incident field because of individual dipoles that are formed by the incident field, and from which you write down the dielectric permittivity. This is what H.A. Lorentz gave back in 1909 for a system of atoms and molecules. But then for us, the resonant units need not be atoms or molecules. They could be larger objects too, but smaller than the wavelength. They could be collections of small antennas. And if you think about it as an electrical engineer and replace these atoms by small antennas, you would say that this is the equation for the force damped oscillator equation for the current in an antenna. And you will end up getting very similar responses for the equivalent dielectric permittivity. And similar things can also be written down for the magnetic permittivity. Okay. Now, one of the simplest metamaterials, just to quickly introduce you to this, is actually a wire array, just a simple wire array. You could have electric fields when you have radiation incident on this wire array. Let's say that the electric field is polarized in this direction, vertical direction. It would induce currents in these wires in this direction. But what happens? The wires are not there everywhere. So the wires are very thin. They are spaced much closely compared to the wavelength. So the electromagnetic field does not know that there are not wires everywhere. It doesn't know the shape, size, distribution, etc. of the wires. It only says, oh, there is a rough amount of conducting medium, the conducting electron density is so much, and the conducting electron density actually reduces by the volume filling fraction of the wire, and that can be very small. Another effect that you can also be used is that these wires, if they are very thin, they have a lot of inductance. Inductance is a inertial effect, just like mass is an inertial effect. Mass prevents change of speed, induction prevents change of currents. So you can actually think about that inductive effect as coming into the effective mass of the charge carrier wire. So if you, this is a nice way of thinking about the plasma frequency of effective plasma frequency of this composite, which depends on the ratio of the effective number density to the effective mass of the charge carrier. And these numbers now depend only on the geometry, and you can actually end up getting plasma frequencies anywhere from the ultraviolet frequency which metals typically have down to just a few gigahertz. You can make a plasma wave. Similarly, you can also look at the magnetic permeability. You can, for example, you just take a stack of metallic cylinders, and if you put an magnetic field incident on this, such that the magnetic field is along the axis of the cylinders, it will induce circulating fields around these cylinders. So there is induction. These cylinders have a finite inductance, and if you make the cross section of the cylinder such that there are gaps for the current carrying wire, current carrying path, then you end up giving it a capacitance, and what you have is a resonant LC circuit. Each cylinder behaves as a resonant LC circuit, and that would have a response like, that magnetization which sets in will respond, will give a response as a magnetic permeability. It will again look resonant about the resonant frequency given by the 1 by square root LC for the circuit, and the imaginary part of the magnetic permeability will shoot up, which represents the dissipation. Now I go on and talk about making a perfect absorber. In physics, you see, we are all talking mainly about optical refractive index most of the time. And we say that the imaginary part of the refractive index would represent the level of dissipation, absorption in the medium. So let us see what happens if you keep on making the levels of absorption in the medium very high. The imaginary part of the refractive index, if you make it very large, in fact take it to infinity, you will find that the reflection coefficient, this is the Fresnel reflection coefficient from the surface of a flat surface of the medium, it just goes to 1. The wave does not enter the absorbing medium at all in order to get absorbed. So it is not enough just to make the absorbing property more. You have to do something more than that, which is something electrical engineers know all the time. They do it all the time. They say that you should match the impedance. The input impedance of this device, of this structure, of this medium should be the same as the impedance of this. And to do that, what you need to do is to make this ratio mu by epsilon go close to 1. These are all relative permittivity and permeabilities that I talked about. So we now have a way of manipulating the magnetic permeability and the dielectric permittivity by metamaterials. Some examples I had shown. So can we use that to manipulate these two numbers at optical frequencies? At optical frequencies, remember, the magnetic permeability of all materials is just 1. There is no magnetic response at optical frequencies. So can we do that using structured materials instead? That was the question we With microwaves, you do that by various means. These are very old ways of doing it. If you go into an anechoic chamber, you'll see a microwave absorbers like that. It is just an impedance matching structure where you put very little material here from top as the wave comes in, and it put in more and more amount of absorbing materials as the wave proceeds. So, using this idea of impedance matching, a perfect absorber was first demonstrated in 2008 by the group of Tirupati in Boston College. What they said was, I have a structure here which is an electrical resonator. So if you put a radiation on it with the electric field in the vertical direction, it will drive currents around these loops. These two loops are there. There are capacitances. It's an LC circuit. And now if you take this structure and stick it on the front side of a copper backed plate. Suppose you have a plate. On one side you put your structure, and on the back side you coat it with a conducting strip like that. So then you would actually be able to drive currents in one direction on this, and because of image currents on this, it will loop back through the back, and you would actually create a magnetic, magnetization inducing current loop across. So using that, they demonstrated at microwave frequencies about 11 gigahertz, something like about 90%, 95% absorbance, and this is something that was actually a development in the area of metal. So we went about doing the same thing, something similar at infrared frequencies in about 2010. We were doing this work. What we did was to say that the simplest resonator can just be a disk. A disk also has electrical resonances, and we can let the suppose the electric field, electromagnetic radiation is incident from top, light is in, you will actually form dipole resonances on this. And if you put it on top of another metallic film separated by a dielectric film, the charges which are actually induced on this disk will form mirror images on this. Mirror images means the charge sign will also change. Any current distributions which actually flow on this will also be mirror image, but the current is in opposite direction in the ground plane. We call this a ground plane, the second metal layer. And between these two, you can induce currents, so you can induce a magnetic resonance also. So both resonances, if you can design them to have a similar frequency, then you can tune the electric and magnetic frequencies and the relative strength of coupling, so you can actually create optimal impedance matching to the tune. And this can result in strong resonant absorption of radiation. And here are some simulations we did at the time, where you can see that the disk here forms a strong electrical resonator. There are anti-parallel currents which are induced on these two surfaces. On this is the disk, the radiation is from incident from the bottom. There's the disk here, there's the top this metal plate here. And then you can see that all the energy actually feeds into this cavity formed between the disk and the ground plane. And this is how all the dissipation results to give rise to a peak which can be almost like 100% absorbing of infrared. This is how we started. And we actually started making these devices by a combination of deposition and micromaterial processes at infrared frequencies. In this picture, for example, these discs are about 3 micrometers in size and they're spaced apart by 8 micrometers. You have a gold film, a film of zinc sulfide, and these discs which are deposited through what we call a shadow mask. We make a sheet with holes in it, and we put that sheet on top of the substrate and evaporate metal with that, and they will form these nice, which you can see in this image. Now, if you measure the resonant response of this was the band for, these are calculations, this was the band for which it was designed, at which you can see that it has about a 96% absorption in the measured characteristics. These are the measured characteristics on your left, and you can see that peak absorption at very large amounts can be obtained even at middle infrared radiation and the shortwave infrared radiation. We can simultaneously impedance match to several resonances. And what are these resonances? These are the antenna resonances of all these patches which are there. You see, you can have a dipole, you can have a quadrupole, you can have higher order multipoles, and each one of these peaks here represents a certain order of the multipole to which the light couples,
and it is very nicely impedance matched. So this actually also makes us think in terms of classical electromagnetic theory, where you can think of them as perfectly impedance matched antennas. How much time do I have? Okay, then quickly I'll go through. Here is an example of optical optical metamaterial, where you can see that at about 520 nanometers you can get a peak absorption of 96% absorption. So now what we did was we actually changed our pitches and frequencies, etc. Used what is called an interference lithography to make these pattern substrates at sub-micron scale, at about 100, 200, 200 micron size. This we could actually deposit. And you can generate perfectly absorbing systems which are at 1 micron or 0.8 microns, which is literally in the visible. And if you observe what happens to the reflected light, as you go to here, you'll find that this reflected light shows that you can, the reflectivity depends on what is the pulse repetition frequency of the laser which is incident. That is, the total intensity that is incident actually affects the reflectivity. It's a non-linear reflectance that you start seeing, and this, what we said was this because the material is absorbing most of the radiation. So if it absorbs most of the radiation, then it should heat up. So when we heated it up with a heater, we actually saw that the reflectivity falls, and that is simply because this resonance here, which you see, this resonance, this actually shifts with increasing temperature because of high conductivity of aluminum, which changes with temperature. These were made with aluminum, and hence it had a large non-linearity with respect to the temperature. Aluminum itself is not non-linear, but the metamaterial becomes non-linear because of the structure. Similarly, we made the metamaterial of gold, where by a similar technique you can see that these are about few tens of nanometers thick. These and sizes are about 500 nanometers. This bar is 500 nanometers here, and you could induce resonances at 106 microns as well as 532 nanometers, which is like 1:2 ratio. And if you measure the reflectance for picosecond pulses, you actually find that the reflective intensity increases initially, as it should with the incident intensity, but at some point it just cuts off. It just starts going down. And this is something, the reflectivity keeps falling with the incident intensity, and this was something very surprising. And what we did was we measured the nonlinear fluorescence, the multiphoton fluorescence that arises from the defect layers in the zinc sulfide. This is the space of layer in between here. From that we could see large amount of nonlinear responses, the nonlinear fluorescence for multiphoton fluorescence that come. And by using certain self-consistent nonlinear simulations, what we could actually find was it is the Kerr nonlinearity of gold as well as the Kerr nonlinearity of zinc sulfide which actually contribute and shift the resonance with increasing amounts of intensity. Right? The entire resonance shifts because it shifts to a different point. You get a different level of absorption. Now, from here it actually goes up to that. So now, the point is, because these fields are so enhanced in the middle, you find that you can get very much larger responses from the zinc sulfide which is actually sitting in the air. And this is like very very classic, because the reflectivity, the intensity just cannot increase beyond a point. And it is like almost a textbook level plan and it all arises due to the large local enhancements. These are the conclusions. You can design surfaces at will to have whatever absorption and whatever frequencies you like. We have come up with very simple designs to make very large area systems which have these. I have shown you two examples of metamaterial nonlinearities. One was the thermally driven nonlinearity, and another arose due to the non-resonant nonlinearity of the constituent materials. And local field enhancements increase the non-linear effects tremendously. The dielectric zinc sulfide layer intrinsically has 10 power minus 4 times smaller nonlinearity than gold, but to the nonlinear effect it contributes on an equal. This is something that we understood. So these are my acknowledgements for the funding. DRDO has been very generous to us in some of our work, and this is my process of award and my PhD for the grant. These are my collaborators. Sriram Gudala was instrumental in carrying out these two works that I presented. He is a postdoc fellow and he is now in the City College of New York. Govindaya was the PhD student who began this work. He is now thinking another is the optical metamaterials work, now at King's College, King's Military College in Canada. And presently there is one more student working with him on this. Thank you.